Good morning, good afternoon, good evening, and welcome to another science post. This one is called There and Back Again, a Physicist's Tale. I am going to explain how gravity is related to the quantum uncertainty principle, but to motivate this explanation, I first need to provide some historical background. In 300 BC, young Archimedes learned in school that the surface area of a sphere is r squared times 4 pi, as in the radius squared times 4 pi. Classical knowledge of atomism, conservation of energy, elliptic conic sections, and heliocentric models became quite advanced until Hypatia and the Library of Alexandria were burnt in 400 AD. This marked the beginning of 1,000 years of darkness, academically speaking. In 1676, at the dawn of the Enlightenment, Robert Hooke acquainted us with how a harmonic oscillator works. Hooke's contemporary, Newton, built on this intuition and realized in 1687 that the force that causes objects to be heavy is the same force that causes planets to orbit the sun. Hooke and Newton did not really get along because Hooke felt that Newton had taken ideas he had expressed intuitively and formalized them without giving him any credit. And Newton did not like the implication that he had lifted any ideas from anyone else. In 1865, Heaviside, Faraday, and Maxwell realized that the laws of electricity and magnetism implied that space and time were bent by these forces, and that the same would likely be true of gravity. Maxwell also realized that the energy in a substance should be composed of equal parts rotation and vibration. This has become known as equipartition, and this concept connects nicely to Kelvin's application of Helmholtz's fluid dynamics equations to describe atoms composed of complexly rotating and vibrating vortices, an idea which gave way to the more empirically simple and verifiable model provided by Rutherford in 1911. In 1900, Poincaré, 1903, Depreto, and 1905, Einstein wrote the same equation, E equals mc squared. In 1881, Heaviside, 1881, Thomson, 1900, Wien, 1904, Lorentz, and 1904, Hasenöhrl all wrote a similar equation, E equals 3/4 mc squared, based on empirical grounds related to a volume of mass in a black body, while the newer results were based on theoretical grounds that added the effect of a surface of mass to the black body estimate. These people all understood that mass has intrinsic energy because it is composed of a substance that is moving around at close to the speed of light relative to the surrounding space. The discrepancies in their estimate seem to depend on whether or not they used Galilean or Lorentzian Maxwell's equations. And I have another post detailing the differences and applications of different formulations of Maxwell's equations. There's more than one set. So in 1915, Einstein puzzled over what these results meant for gravity with regard to his professor Minkowski's curved spacetime and Mach's principle. This was an ironic investigation into the properties of ether from a man who had gained fame a few years earlier by proclaiming that ether couldn't exist because there was no absolute reference frame. He didn't know that, whereas Michelson and Morley had showed that light doesn't experience etheric drag, similar experiments with particles show where Lorentz invariance breaks down. It makes perfect sense to think about a sort of matter ether, even if a luminiferous ether doesn't make much sense. Between 1915 and 1949, the world wars and the atomic bomb shocked and awed the public with the destructive power of science, and Einstein somehow became the awkward poster boy for this power. Throughout the wars, science transformed into a dangerous, compartmentalized enterprise, which has since been centrally controlled through large laboratories and funding agencies that have steered youthful curiosity towards the very tiny and very abstract, as in quantum chromodynamics, and the unimaginably distant, powerful, and invisible, as in black holes, neither of which have any application in bomb building or in any other discipline. This effectively neutralizes a whole population of smart, capable young people. But maintaining a degree of big picture uncertainty among smart, capable young people seemed wise given the dangers of nuclear proliferation. In 1973, discussions about the temperature of space seen by an accelerated observer on the edge of the event horizon of a black hole produced a description of the Unruh effect. Temperature equals HACK 4 pi squared. HA over CK 4 pi squared. If we connect this cosmic insight to the vortex particles of Kelvin from 1865, we automatically have a description of the cause of a particle's inertia. Despite this rather obvious connection, applying the Unruh effect to the dynamics of fundamental particles never became popular within the physics community. Instead, it was taught as a concept that was untestable so far, therefore we should not speak of it. This is a tendency in physics where they refuse to acknowledge their blind spots, and this distorts the entire field. As a result, the community has been dominated by people who were determined to turn concrete concepts such as spin, color, and flavor into inscrutably abstract and useless ones, further neutralizing the sort of knowledge that smart, capable young people are always driven to acquire. In 1983, related discussions about the holography and entropy of a black hole led to the realization that one could define the smallest possible length and time scales in terms of fundamental constants and then use them to describe the degrees of freedom contained within a volume. Holography was just a complicated way of saying that for vortices large and small, the volume is related to the surface area in a fundamental way. This is something that has been known since the study of objects like Gabriel's horn in the 1700s. Yet, this trend of making simple things seem extremely complex has infiltrated every branch of physics today. It's the way in which the community gains its ability to ask for more funding and which mystifies the topic enough that students are drawn forward with curiosity, wanting to figure out the complex mystery. And they are given so much material to digest that they never really have a chance to sit back and figure out the simple reality underlying all of it. It's a clever system. In 2009, Eric Verlinde pointed out that all of the equations we use in holography and everything seem to be quite consistent with one another. And some people reacted by saying that the consistency is obvious and trivial, while others said it was new and profound. Such is the mercurial nature of a physicist's ego. In any case, when one adds all of these ingredients together and rejects compartmentalized thinking, you end up with a picture of inertia and gravity caused by a substance containing rotational and vibrational motion relative to an absolute reference frame. The inertia of an object is due to the energy required to accelerate a subcomponent which is already moving at close to the speed of light, and the gravity well with which we are familiar from Laplace in the 1700s and from general relativity, the turn of the century, is caused by the internal motion or turbulence, changing the shape or density if you are a Cartesian, of the surrounding space and time. When particles within an object are vibrating, they don't exist at one location all of the time, and the uncertainty of their position is responsible for the curvature of space and time. So while we can see the result of the uncertainty principle written large across the cosmos when Eddington's starlight bends around the sun, we can also see the uncertainty principle in our inability to stop the Zitterbewegung of a fundamental particle. When I compare the formula for the uncertainty principle to the formula for the area of a sphere, I conclude that Planck's constant, h, is simply the area of a sphere with a radius given by the position and momentum of a point in space. To bring this narrative, this historical narrative, around in a full circle, I wonder if Archimedes' geometric understanding of atomism was similar, way back in 300 BC. I found a paper where some people seemed to be making a similar connection, but they do so in the convoluted, overly complex language of the modern physics community. And I've tried to express something similar. Their article was entitled Gravitomagnetism and Non-Commutative Geometry. And I tried to express something similar in the language of tired light, an old idea about the cosmos, but defending the reasoning of this sort of reasoning from those in the physics community who suffer from aphantasia or inability to visualize. It's made me a bit tired and jaded about this, I must say. So in conclusion to this historical journey, climbing the mountain of physics knowledge may seem worthwhile, but the journey will change you, and after seeing the view from the peak, you may wish that you had not been so changed. That's sort of what inspired the title of this post, this Tolkien-esque There and Back Again, a physicist's tale. If I were to try to tell this same story without mentioning any men at all. I'd write about Hypatia of Alexandria instead of Archimedes. I'd write about Émile du Châtelet and about Sophie Germain instead of about Schrödinger and Heisenberg. I'd write about Marie Curie, Lisa Meitner, Mileva Marek, Einstein's wife who helped him write his papers in his miracle year. And last but not least, I would talk about Emmy Noether. I should do that, and I think the result would be amusing, that you could literally write the history of physics without mentioning a single man. It tells you something about how history is recorded. But instead of doing that, I would like to illustrate the state of modern physics by explaining some subjects, starting from well-substantiated statements and ending with wild speculations that many physicists today accept as fact. So this is supposed to be a little bit funny, but I don't know how my delivery will be. Eureka! The intellectual ejaculated. The night sky is black with dots of light. The light must have come from far away, because faraway things that are moving away from us, because otherwise, how did the darkness get there? If they are moving, then we are probably moving too, and if we are all moving in the same general direction, then there must have been an origin point for everything. And there must have been a giant explosion of a cosmic egg, and since explosions distribute matter unevenly, the egg must have blown up like a balloon before it exploded. And since there seems to be a uniform temperature across the sky, the balloon must have blown up at faster than the speed of light, at a rate of a light year within a few seconds. This is the present Lambda CDM model of the universe, and it just won yet another Nobel Prize. This is too fun. I have to try another one. Gravity pulls us down to Earth, and a fast-moving ball that is pulled by a string will go around in a circle. There are some lights in the sky that appear to be traveling around the sun in the same way that our planet is. So we are all being pulled towards the sun, and the force responsible for this is also gravity. There are some really small units with a length of 1 × 10⁻35 meters that make up everything, and they exist in a spin foam that we will not ever be able to measure. But because of loops of action occurring in the foam, we know this causes gravity, because we were able to describe a foam that obeys the same laws that work on larger planetary scales, but which fail on galactic and supergalactic scales. This is a theory that people actually study. I think it has something to do with polymers. I don't know. I'll do another one. I'm not going to skip out on any branch of physics here. Big things are made up of little things. The littlest things which we can measure in a stable configuration can be collided with each other, and a bunch of weird, unstable stuff comes out. There are, for example, particles that are produced in pairs of opposites, and these pairs of opposites disappear into thin air when they interact with one another. They act as a single unit, yet seem a bit distributed in space. The members of these pairs have never been observed in isolation. Therefore, we can conclude that the littlest things which we can measure in a stable configuration are composed of the members of these pairs in isolation, and the structure of their organization is a form which has never been observed. This is the story of quarks organized according to the Eightfold Way, which is frankly bizarre in my opinion, that this is taught so widely. It's like the biggest waste of time ever. And I'll do even another one. Let's see. A model of gravity predicts the existence of invisible things in outer space. The model predicts that these invisible things will cause visible things to move in certain ways. People claim to have taken photographs of these motions, but the photos are very blurry. They are constructed in a reconstructed, dubious sort of way, and one could come up with several explanations for what is observed. These invisible things absolutely exist because our models of gravity are so fantastic. Even though the models of gravity don't predict the shape of galaxies or the distribution of galaxies. Let's take this one step further. We can measure the effect of these invisible things colliding in unimaginably distant star systems by watching how the waves they create cause laser beams to shrink and stretch on Earth. Even though we tried to see a similar effect in the Michelson-Morley experiment, and it didn't work. So LIGO is an expensive multi-billion-dollar experiment in the US called a gravitational wave observatory, and it is basically a giant version of the Michelson-Morley experiment, but they say it will give a different result because general relativity and special relativity don't treat space and time in the same way. There's a lot of hand-waving in their explanation. I think they built it because they wanted a really good seismometer, but they decided to put up a bunch of hokey theoretical smoke and mirrors to justify the project. I mean, really, guys, come on. I should stop, but there are just too many of these. Most of the systems we measure today obey the law of conservation of energy. All of the systems obey the law if we are generous with how we define energy. The smallest things we measure obey the law on average, but there are weird particles that briefly pop into and out of existence, and while they exist, they violate the law of conservation of energy. Some of the small things that we measure don't obey conservation of energy on average, so we need to invent a new particle to make the system obey the law. The particle is so small that no one can measure it. But if you try hard enough, you can actually measure this hypothetical particle, even though it is hard to rule out the possibility that the measurements were caused by something else. Come on, physics, you can do better. If you don't have a problem with photographs of invisible things, there really isn't anything I can say to help you. At a certain point, theoretical physicist is not a profession, it is a diagnosis. If you or someone you love is considering studying physics, please get help. Thank you for watching. I hope you tune into my next videos. I won't be quite as mean as I was in this one.